In the vast silence between galaxies, light carries a secret it refuses to fully reveal. For nearly a century, astronomers believed they had deciphered the rhythm of the cosmos, that the universe was expanding, and that expansion could be measured, predicted, and trusted. But the more precisely they measured, the less the universe seemed to agree. Today, a quiet crisis echoes through modern cosmology, one that could rewrite the very laws we thought governed reality. It's called the Hubble Tension, the growing conflict between two ways of measuring how fast the universe is expanding. Both methods are right. Both are based on solid physics, and yet they disagree by an amount too large to dismiss as error. If the universe itself could speak, this would be its contradiction, a disagreement written in the language of light. The story begins almost a century ago, when Edwin Hubble, working at the Mount Wilson Observatory, pointed his telescope toward the Andromeda Nebula. What he found transformed astronomy forever. The faint smudges of light in the night sky were not nearby clouds of gas, but entire galaxies, vast islands of stars drifting away from us. The universe, he realized, was expanding. By comparing the light from distant galaxies, Hubble noticed something profound. The farther a galaxy was, the faster it seemed to move away. This relationship, now known as Hubble's law, became the foundation of modern cosmology. The constant that describes it, the Hubble constant, tells us how fast space itself stretches with time. It's a simple number with enormous meaning. It defines the age, size, and ultimate fate of the universe. But simplicity, in cosmology, is always deceptive. For decades, scientists refined the Hubble constant with better telescopes and more sophisticated techniques. They measured supernovae, Cepheid variable stars, and the faint afterglow of the Big Bang known as the cosmic microwave background, CMB. Each new method promised a clearer picture, until around 2016, something unexpected emerged. The values didn't match. Measurements made using nearby galaxies and supernovae, the local method, gave a Hubble constant of about 73 kilometers per second per megaparsec. Meanwhile, measurements using the CMB, a relic of the early universe observed by satellites like Planck, gave a slower rate, around 67. The difference may sound small, but in cosmology it's seismic. It means that either the early universe behaved differently than we think, or that something fundamental is missing from our model of physics itself. Scientists tried to explain the discrepancy away. Perhaps there were calibration errors, or overlooked dust, or statistical quirks. But as data grew stronger, the excuses evaporated. The tension didn't disappear, it sharpened. By 2019, the disagreement had reached a 5 sigma level, the statistical threshold at which physicists typically declare a discovery. In other words, the mismatch was no longer noise. It was a signal, and signals demand explanation. Was the universe expanding faster now than before, as if cosmic acceleration itself had changed over time? Was there an unknown form of energy, an early dark energy, that pushed the universe apart more strongly in its youth? Or had we simply misunderstood gravity on the largest scales? Whatever the answer, it would not be small, because in cosmology, a small number can break everything. The Hubble tension forces us to confront an uncomfortable possibility, that the standard model of cosmology, the framework that explains everything from the Big Bang to the cosmic web, may be incomplete. It challenges our assumptions about dark matter, dark energy, and even the geometry of space-time itself. For the first time in decades, the universe is no longer behaving according to our equations, and scientists are being forced to imagine that the cosmos might be more complex, more dynamic, and more surprising than the model we built to describe it. And yet, this is not the end of understanding. It's the beginning of a deeper mystery, one written not in myths or metaphors, but in photons traveling across billions of years to tell us that something, somewhere, doesn't add up. The question is not whether the universe is expanding, it's why it's expanding faster than it should. The story of cosmic expansion began not with the Big Bang, but with glass and patience. In the 1920s, the world's largest telescope sat atop Mount Wilson in California, a 100-inch mirror reflecting humanity's curiosity back at the stars. It was here that Edwin Hubble and his colleagues began to map the universe beyond imagination. Until then, astronomers believed the Milky Way was the entire cosmos, a self-contained island of stars adrift in an endless void. Then came a faint pulse of light from the Andromeda Nebula. Through careful measurements of variable stars known as Cepheids, Hubble calculated that Andromeda lay far outside our galaxy, millions of light years away. Overnight, the known universe expanded from one island to a cosmic archipelago. But Hubble's true revelation was not distance, it was motion. By comparing the redshift of galaxies, the way their light stretched to longer, redder wavelengths, he realized they were moving away from us. The farther they were, the faster they seemed to recede. Space itself was stretching. The static universe of Newton was dead. Einstein's dynamic universe was born. Even Einstein, who had introduced the idea of a cosmological constant to keep the cosmos static, was stunned by Hubble's results. "My greatest blunder," he later called it, though modern cosmology would eventually redeem that constant under a new name: dark energy. The relationship Hubble uncovered became the Hubble law, expressed simply as V in h0xd, velocity equals distance times the Hubble constant. That constant, h0, became one of the most important numbers in science. It defined the expansion rate of the universe and, by extension, its age. If the universe has been expanding at a steady rate, then its age can be estimated as the inverse of h0. A larger value means a younger universe, a smaller one, an older cosmos. But the early decades of cosmology were anything but certain. Observations were limited, instruments crude, and theories fragile. Initial estimates of h0 varied wildly, from 500 to 50 kilometers per second per megaparsec, suggesting a universe that might be younger than Earth itself. Such contradictions revealed how far astronomy still had to go. Over time, new instruments sharpened the picture. Radio astronomy emerged, capturing signals invisible to optical telescopes. Satellites like COBE and WMAP later mapped the faint afterglow of the Big Bang, the cosmic microwave background, giving cosmologists a way to measure the universe not just locally, but globally. The CMB carried the fingerprint of the early cosmos, encoded in subtle fluctuations that revealed its density, composition, and curvature. By the 1990s, these two measurement strategies, local and cosmic, seemed to converge. Using Cepheid variables and type Ia supernovae, astronomers refined Hubble's ladder of distances, while CMB observations anchored the model of a flat, accelerating universe dominated by dark matter and dark energy. The lambda cold dark matter (LCDM) model became the new standard, elegant, predictive, and successful at explaining nearly every large-scale observation. For a time, it appeared that cosmology had entered its golden age, a time of precision rather than speculation. h0 was no longer a mystery. It was a number waiting to be measured to the second decimal place. Then came the paradox. When NASA's Planck satellite measured the CMB in extraordinary detail, it derived a value of h0, 67.4 plus 0.5 km/0 MPC, implying a universe about 13.8 billion years old. But when astronomers measured nearby galaxies using the Hubble Space Telescope and other observatories, they obtained a value near 73 km/s MPC, corresponding to a universe nearly a billion years younger. A billion years missing or misplaced may not sound catastrophic, but for cosmology it was. It meant that either the early universe was expanding more slowly than it should have been, or that the late universe was expanding faster. In either case, the standard model, once thought unshakable, no longer fit all the data. The problem, now known as the Hubble Tension, became the center of one of the most intense scientific debates of the 21st century. Every new telescope, every recalibration, every statistical correction only deepened the mystery. Each side defended its data with confidence, yet both could not be right. If the local measurements were correct, something must have changed in the fabric of space itself since the cosmic microwave background was formed. Perhaps an unknown form of energy influencing expansion in the intervening billions of years. If the CMB measurements were correct, then the nearby universe must be hiding a systematic bias, an unaccounted distortion in how distances or redshifts are calculated. Neither explanation satisfied everyone. The beauty of the crisis lies in its subtlety. Nothing about the Hubble tension shouts error. Everything whispers curiosity. It's not a mistake in a telescope mirror or a missing line in an equation. It's a discrepancy born from precision, the kind of problem that only arises when science works almost perfectly. Cosmology has seen crises before: the ultraviolet catastrophe, the missing neutrinos, the dark energy surprise. Each, in time, opened new windows on reality. The Hubble tension may be another such window, one that invites us to reconsider the very scaffolding of space and time. For now, the universe remains caught between two clocks. One, ancient and cosmic, ticks from the fire of the Big Bang. The other, local and luminous, beats to the rhythm of nearby galaxies. They both tell the story of expansion, but they refuse to tell the same time. And somewhere in that disagreement may lie the next great revolution in physics. To measure the expansion of the universe is to measure time itself stretching. But time does not stretch evenly, and light, our only witness, does not travel unchanged. Every method that seeks to define the Hubble constant depends on decoding how the universe has distorted its own message. Astronomers built what they call the cosmic distance ladder, a hierarchy of techniques to measure distances across the cosmos. Each rung depends on the reliability of the one below it. The first rung begins close to home, with parallax, the apparent shift in the position of nearby stars as Earth orbits the Sun. Parallax gives absolute distances out to a few thousand light-years, forming the foundation for everything that follows. The next rung uses Cepheid variable stars, luminous giants that pulsate in a predictable pattern. Their brightness varies with a period directly related to their intrinsic luminosity. By comparing how bright a Cepheid appears from Earth to how bright it should be, astronomers can calculate its distance. This method allowed Hubble to discover the expansion of the universe, and a century later, it remains one of the cornerstones of cosmic measurement. Farther out, astronomers rely on Type Ia supernovae, colossal stellar explosions that occur when a white dwarf reaches a critical mass. Because these events always release nearly the same amount of energy, they act as standard candles visible across billions of light years. By measuring their apparent brightness, scientists can infer their distance and thus the rate at which galaxies are receding. This local ladder provides a direct empirical measure of expansion, the rate at which galaxies around us are moving away right now. When calibrated carefully, it yields a Hubble constant around 73 km/s MPC. But there is another ladder, one that reaches not outward, but backward in time. The cosmic microwave background, CMB, first detected in 1965 by Penzias and Wilson, is the oldest light in the universe, a fossil glow from 380,000 years after the Big Bang. It carries the imprint of density fluctuations, tiny differences in temperature that mark where matter was slightly more or less concentrated. Those fluctuations have grown over billions of years into the galaxies and clusters we see today. By analyzing the pattern of these temperature variations, missions like Planck and WMAP reconstruct the universe's entire composition: dark matter, dark energy, baryonic matter, and radiation. From those parameters, the expansion rate can be inferred, not directly observed, but predicted based on the physics of the early universe. This gives a lower value for H0, around 67 km/s MPC. So there are two clocks: the local clock of galaxies and supernovae, and the cosmic clock of the early universe. Each measures the same expansion, yet they disagree, as though the universe aged at two different speeds. Initially, cosmologists suspected an error somewhere on the distance ladder. Cepheids are affected by dust and metallicity. Supernovae may vary subtly depending on their environment. Every calibration introduces potential bias. But as measurements improved, particularly from the SH0ES collaboration led by Adam Rees, the tension persisted. The team's 2021 results confirmed a value of H0, 73.0 plus 1.0, a precision of less than 2%. Planck's precision was similar. The gap was no longer statistical noise. Other techniques joined the debate. Observations of gravitational lensing, where massive galaxies bend light from background quasars, provided an independent route to H0, and they, too, leaned toward the higher local value. Meanwhile, baryon acoustic oscillations, ripples in the large-scale distribution of galaxies, aligned with the lower Planck result. The deeper the measurements, the wider the chasm grew. To resolve it, scientists began to question whether our understanding of cosmic history might be incomplete. Perhaps the early universe contained something unexpected, a burst of energy or a new particle species that briefly altered expansion before fading away. This idea became known as early dark energy, a hypothetical form of energy that might have inflated space for a short time between recombination and structure formation. If such an energy existed, it could increase the predicted value of H0 from the CMB side, bringing it closer to the local result without contradicting other observations. Several models have been proposed, some involving scalar fields similar to those that drove cosmic inflation, others invoking modifications to neutrino physics. Yet so far, none fully solve the problem without creating new inconsistencies elsewhere. What makes the Hubble tension fascinating is not its magnitude, but its stability. Most anomalies in science shrink under scrutiny. This one refuses to. Every telescope that remeasures distances, every team that reanalyzes the CMB, finds the same stubborn disagreement. The universe seems to insist that we are missing something fundamental. Even the James Webb Space Telescope, JWST, designed partly to reobserve Cepheids and standard candles with unprecedented precision, has begun to weigh in. Its infrared sensitivity allows astronomers to see through interstellar dust that once obscured optical measurements. Early JWST observations have confirmed the higher local expansion rate, strengthening the tension rather than resolving it. This is where science becomes philosophy by other means. How can two truths coexist in one universe? How can the cosmos reveal precision, yet deny harmony? The answer may lie not in the data, but in the assumptions underlying the models themselves, in the equations that connect the early and late universe. Perhaps the expansion is not uniform. Perhaps space-time itself changes its properties over cosmic time, as though the constant of gravity or dark energy evolves. Or perhaps the tension is not in the universe at all, but in us, in our insistence on describing cosmic behavior with human notions of symmetry and simplicity. In every scenario, the Hubble tension serves as a mirror. It reflects the limits of our methods and the boldness of our curiosity. Science does not fear contradiction. It feeds on it. Each discrepancy is a message encoded in light, urging us to look deeper. When Edwin Hubble first plotted his line of recession velocities, the data were rough, uncertain, incomplete, yet they revealed a truth no one expected. A century later, the line remains, now drawn with exquisite precision, and yet its slope still eludes us. The cosmos is expanding, yes, but perhaps not in the way we think. When scientists say the universe is expanding, it's easy to imagine galaxies flying apart like shrapnel from an explosion. But that picture is wrong. Nothing is moving through space. Space itself is stretching. The galaxies are carried along by that expansion, like coins glued to the surface of a balloon as it inflates. The farther apart they are, the faster they seem to drift. This idea comes from general relativity, Einstein's theory that gravity is not a force but the bending of space and time. When matter and energy fill the universe, they curve space in such a way that it must either expand or contract. It cannot remain perfectly still. Einstein once tried to resist this conclusion by adding what he called the cosmological constant, a term that balanced gravity with a gentle outward pressure. He thought it would hold the universe steady, but after Hubble's discovery, he abandoned it. Ironically, decades later, that same constant returned to cosmology, renamed dark energy, the mysterious pressure that drives the universe to expand faster and faster. Dark energy is now believed to make up about 70% of the entire cosmos. It acts like an invisible hand pushing galaxies apart. The rest is dark matter, unseen mass that pulls everything together through gravity, and ordinary matter, the kind that makes stars, planets, and us, which accounts for less than 5%. In this delicate tug of war, The rate of expansion, known as the Hubble rate, is like the pulse of the universe. It tells us how these competing forces balance at any given moment. But the problem, the reason for the Hubble tension, is that the pulse we measure today does not match the one predicted from the early universe. It's as though the heartbeat of the cosmos has changed tempo without warning. To understand how, imagine rewinding the universe back to its first seconds. Matter was dense, hot, and uniform. The tiny ripples that we now see as galaxies were microscopic variations in that early plasma. As the universe expanded and cooled, those ripples grew. The physics governing this process should connect the early and late universe seamlessly. If you know the density of matter, radiation, and dark energy, you should be able to predict the current rate of expansion exactly. But the numbers do not add up. That's why many physicists now suspect something subtle is missing from our understanding of cosmic evolution. One possibility is that dark energy itself has changed over time, that it was stronger in the early universe than it is now. This idea is sometimes called early dark energy. It suggests that before galaxies fully formed, a temporary burst of repulsive energy sped up expansion, leaving an imprint that still affects how fast the universe grows today. Another line of thought questions the nature of dark matter. What if it interacts not only through gravity, but also weakly with radiation, or itself? Such interactions could have altered the structure of the early universe in ways that affect present-day measurements. Researchers are testing these ideas using high-resolution simulations that model how gas, light, and invisible matter move through cosmic time. There is also a more radical possibility, that gravity itself behaves differently across vast distances. Einstein's equations have passed every local test, from falling apples to the orbit of Mercury, but they have never been tested on the scale of the entire universe. Modified gravity theories, such as those that slightly change how space curves or how time flows, could naturally create an expansion rate that evolves in unexpected ways. These are not wild speculations. They are mathematical possibilities grounded in modern physics. Meanwhile, telescopes continue to push deeper into the cosmic past. The James Webb Space Telescope, JWST, with its infrared eyes, has already found galaxies so massive and mature that they seem impossible to exist so soon after the Big Bang. If these findings hold, they hint that the universe evolved faster than our models predict, another clue that something fundamental may need revision. One of the most striking pieces of evidence comes from the way galaxy clusters form. These clusters are the largest gravitational structures in the universe, containing thousands of galaxies bound by dark matter. Their distribution and number depend directly on how fast the universe expands. When researchers compare observations with simulations based on the slower expansion rate, the numbers fall short. There are more clusters in reality than expected. Once again, the cosmos whispers that its growth was quicker, its early years more active than our equations allow. Still, most scientists remain cautious. The Hubble tension could, in principle, result from something as simple as bias in distance calibration. Measuring the brightness of a star billions of light years away is not a straightforward task. Even tiny uncertainties, a misjudgment in dust absorption, or a slight misreading of metallicity, can ripple into a significant difference in the final number. The challenge is that both sides, early and late, are now so precise that no obvious error remains visible. That's why the Hubble tension is often described as a beautiful problem. It doesn't threaten to break cosmology. It challenges it to evolve. It's the kind of problem that has historically led to revolutions. In the past, the ultraviolet catastrophe led to quantum mechanics. The orbit of Mercury led to general relativity. This new disagreement may be pointing toward the next great leap, perhaps a unified theory that connects the quantum world with cosmic expansion. To reach that level of understanding, scientists are combining multiple approaches. Observations from radio telescopes such as the Square Kilometre Array will trace neutral hydrogen across cosmic time, mapping how structure formed and evolved. The Euclid mission from the European Space Agency is mapping billions of galaxies to measure how dark energy shapes their clustering. And JWST continues to peer into the first few 100 million years of existence, looking for the moment when the first light turned on. Each dataset adds a new layer to the mystery, The hope is that when all are combined, light, radio, gravity, a single consistent picture will emerge. Perhaps the Hubble constant isn't constant at all, but a dynamic property, changing with the hidden physics of the cosmos. For now, the tension stands as both a warning and an invitation. It warns us that our most trusted model of the universe, elegant, logical, and widely celebrated, may only be an approximation, and it invites us to imagine something grander, a cosmos still full of secrets, still capable of surprise, still teaching us humility through numbers we thought we understood. The universe, it seems, is not a solved equation. It is a living experiment, one where even the constants can change. To solve the mystery of the Hubble tension, scientists are treating the cosmos like a vast crime scene frozen in light. Every photon that reaches a telescope carries evidence, a clue about when and where it began its journey. The problem is that the evidence is ancient, distorted by time and written in a language of wavelengths and spectra that must be carefully decoded. Modern cosmology is built on that decoding. Each new telescope is like a new instrument in a forensic lab, tuned to detect a specific fingerprint of the universe. The James Webb Space Telescope, JWST, is one of the most powerful of these tools. It was designed not just to look far away, but to look back in time, into an era when the first galaxies were forming from cold hydrogen clouds. What Webb has already shown astonishes even the most cautious scientists. In its first months of observation, it spotted galaxies so bright and massive that, by conventional timelines, they shouldn't exist yet. These galaxies appear to have formed within just 300 million years after the Big Bang, a blink of an eye in cosmic history. According to current models, there should not have been enough time for so many stars to form and cluster together so densely. This finding feeds directly into the Hubble tension. If galaxies formed faster than predicted, that means the universe itself was evolving faster, which could explain why today's expansion rate appears higher. In other words, the universe may have always been running ahead of schedule. To check that possibility, JWST focuses on the faintest, reddest galaxies, those whose light has been stretched the most by expansion. These are not just ancient, they are the first. By measuring their brightness and chemical makeup, astronomers can estimate how much matter had already condensed at that early time. The results suggest a universe that was more efficient at creating structure than our equations allow. That, in turn, might mean that something about dark energy or dark matter acted differently in those years. At the same time, missions like Planck, WMAP, and now Euclid are mapping the universe from a completely different angle, not by looking at light, but by tracing the invisible scaffolding of gravity. This cosmic map shows where matter, both visible and dark, has clumped together over billions of years. Comparing those maps with how galaxies actually move gives another measure of expansion. One of the key ideas behind this method is called gravitational lensing. When light passes near a massive object, like a galaxy cluster, its path bends slightly. By analyzing how background galaxies appear distorted, scientists can estimate how much matter lies between us and them. This technique has confirmed that about 85% of all matter in the universe is invisible. But it also helps measure how the rate of expansion has changed with time. Euclid, launched by the European Space Agency, will soon observe billions of galaxies across more than 1/3 of the sky, its goal, to measure how quickly cosmic structures have grown under the influence of dark energy. If the Hubble tension arises from something changing in that balance, if dark energy has grown stronger or weaker, Euclid's survey should reveal it. Meanwhile, NASA's Nancy Grace Roman telescope will join the investigation later this decade. Equipped with a field of view hundreds of times larger than Hubble's, it will measure thousands of supernovae and millions of galaxies. Extending the distance ladder with unmatched precision, Roman's data will overlap with Webb's deep field observations, bridging the gap between local and early measurements, the very space where the tension lives. This collaboration between telescopes represents a new era in cosmology. In the past, each mission acted like a separate investigator. Now, the universe is being interrogated by a network of instruments: infrared, optical, radio, and gravitational. Their combined goal is not just to describe what is happening, but why. But science is cautious. For every new dataset, there are dozens of independent checks. Astronomers reprocess raw data with different algorithms, cross-compare calibration sources, and even simulate artificial galaxies to see if their software can recover the right values. The goal is to ensure that what they see is real, not a shadow cast by human bias. Despite this care, the evidence remains contradictory. JWST's early results support faster cosmic evolution. CMB data insists otherwise. Each new observation sharpens both sides of the divide. This tension, though frustrating, is the heartbeat of science itself. Progress made through disagreement, truth approached through error. There is also a poetic irony here. The same telescope named after Edwin Hubble, whose discovery of expansion rewrote the universe, now hosts a debate about how fast that expansion truly is. Hubble once turned galaxies from distant smudges into entire worlds. Webb and its successors may turn those worlds into keys for understanding time itself. Even beyond physics, this question touches something deeper. The age of the universe is not just a number, it's the story of everything that has ever existed. A change in that number reshapes the scale of cosmic history. If the universe is younger than we think, then the first stars, the first planets, the first molecules of life all appeared in a shorter window than imagined. That would make the emergence of complexity, and possibly life, an even more remarkable phenomenon. The Hubble tension, then, is not just about mathematics. It's about perspective. It forces us to ask whether our picture of time, smooth, continuous, and universal, might be too simple. If different parts of the cosmos experience expansion differently, then cosmic time may not flow uniformly everywhere. In that case, the universe we see could be layered in history, like a symphony played on instruments that are slightly out of tune but still harmonize. In the next phase of research, scientists hope to measure expansion using standard sirens, signals from merging black holes and neutron stars detected by gravitational wave observatories. These events create ripples in space-time itself, and their brightness and frequency give a direct measure of distance independent of light. If standard sirens confirm one side of the Hubble tension, the mystery may finally tip toward resolution. For now, though, the case remains open. The cosmos is speaking, but in two voices, one whispering from its ancient fire, the other echoing from its living galaxies. Somewhere between them lies the truth, waiting to be heard. If the Hubble tension is a crack in our understanding of the present, then it also echoes into the future, because how we measure expansion today determines how we imagine the universe will end. The Hubble constant is not just a number, it's a prediction of destiny. A faster expansion points toward a colder, lonelier fate. A slower one hints that gravity might still one day pull everything back together. The argument, therefore, is not only about precision, it's about the ultimate direction of time. In the simplest version of the story, the universe will continue to expand forever. Galaxies will drift farther apart until their light no longer reaches one another. Stars will die, planets will freeze, and black holes will evaporate into silence. Astronomers call this the heat death, not because it is hot, but because all heat, all energy differences will have evened out. It's a future without contrast, where nothing new can happen. But the tension in the expansion rate complicates this vision. If the universe is growing faster than expected, it could mean that dark energy, the mysterious pressure driving expansion, is not constant. It might be getting stronger with time. If that is true, the final act of the cosmos could be far more violent, the Big Rip. In that scenario, space itself accelerates without limit, eventually tearing apart galaxies, then solar systems, then atoms. Everything bound together by gravity or electromagnetism would be undone. This idea sounds extreme, yet it is consistent with some interpretations of the data. The Hubble tension might be the first faint whisper of that instability, a sign that dark energy is not a steady background but a dynamic, evolving field. If it changes even slightly over billions of years, the universe's long-term fate changes completely. There are, of course, alternative possibilities. Some models suggest that dark energy might eventually reverse its sign, turning from repulsive to attractive. If that happens, expansion would slow, stop, and then reverse. The cosmos would contract, galaxies rushing back toward one another in what theorists call the Big Crunch. This collapse might end in a singularity, or it might rebound into a new Big Bang, beginning another cosmic cycle. In that view, the universe breathes, inhaling and exhaling across eons. The truth is that no one yet knows which path we are on. Observations hint at an accelerating universe, but the strength and cause of that acceleration remain uncertain. If the Hubble tension turns out to be real, it may force us to rewrite the timeline of cosmic acceleration entirely. To probe this mystery further, astronomers are not just looking outward, they are also looking inward, into the laws of physics themselves. Every cosmic model rests on constants that we assume never change: the speed of light, the strength of gravity, the charge of the electron. But what if one or more of these constants has evolved slightly since the universe began? A minute shift in any of them would ripple through cosmic history, altering everything from the birth of stars to the rate of expansion. Some laboratory experiments are already testing this idea. Ultra-precise atomic clocks on Earth can detect changes in fundamental constants as small as 1 part in a quadrillion. So far, no variation has been found. But the search continues. It's possible that the universe hides its secrets not in grand gestures, but in the smallest differences, subtle enough to escape notice for billions of years. The Hubble tension is therefore more than an observational puzzle. It may be a diagnosis, a sign that our current theory, elegant as it is, describes only part of reality. Cosmologists sometimes speak of the universe as a machine that runs on equations. But the closer we look, the more that machine feels like a living system, complex, self-adjusting, and full of hidden feedback. Even the fabric of space-time may not be continuous. Some modern theories, especially those combining quantum mechanics with gravity, suggest that space and time emerge from deeper, discrete structures, networks of information that behave like code. In such a framework, expansion might not be smooth at all. It could fluctuate, adapting to the density and energy of the cosmos, in ways that appear irregular when viewed from our scale. If that sounds abstract, it's worth remembering that every major leap in science once seemed implausible. The Earth orbiting the Sun, time running slower at high speeds, the idea that empty space could have energy. Each was unthinkable, until evidence made it undeniable. The Hubble tension could be the next step in that tradition, the moment we realize that the universe is more flexible, more alive than our equations allow. Meanwhile, telescopes continue to collect photons from the edges of time. JWST, Roman, Euclid, and others will build a three-dimensional map of cosmic expansion, not just across space but through history. This map will show how galaxies clustered, how voids widened, and how the rhythm of the universe changed with age. From that rhythm, scientists will infer the true behavior of dark energy, whether it hums steadily or changes pitch as the universe plays on. Perhaps one day the Hubble tension will vanish, resolved by a new model that unites early and late measurements under one coherent story. Or perhaps it will deepen, revealing cracks that lead to a greater theory, one that merges gravity, quantum fields, and the flow of time into a single understanding. Either outcome will be progress, because both require us to look more closely at reality itself. For now, the expansion continues. Every second, every galaxy drifts a little farther, carrying its light toward the unknown. The same expansion that separates stars also allows observers like us to exist, suspended between creation and extinction. The tension in the data is mirrored by the tension in our own nature, the desire to measure the infinite, to name what cannot yet be known. In the end, the universe is not only expanding in space, it is expanding in meaning. Each new discovery stretches the boundary of what we can imagine, and somewhere, beyond the reach of even the deepest telescope, the answer already exists, waiting for us to catch up. Every era of astronomy begins with a new way of measuring distance. Galileo gave us the telescope, Hubble gave us redshift, and now JWST and the coming generation of observatories promise to give us time itself, not as an abstract idea, but as something that can be measured, mapped, and tested. The Hubble tension is not just an error to be fixed. It is a compass pointing toward the next frontier of precision cosmology. NASA's current strategy treats the universe as a giant experiment. Instead of asking one question at a time, how fast is it expanding? The new missions ask dozens simultaneously. They compare light, gravity, and motion to see whether they tell the same story. When they do not, the differences reveal the hidden physics that lies between. The Nancy Grace Roman Space Telescope, expected to launch within this decade, is the flagship of that plan. Roman will survey millions of galaxies using supernovae and gravitational lensing to create the most detailed expansion history ever recorded. Unlike earlier telescopes that looked deep but narrow, Roman will look wide, scanning a vast portion of the sky in high resolution. Its strength will not be in a single discovery, but in numbers so large that statistical noise becomes silence. In that silence, truth emerges. At the same time, the Vera Rubin Observatory on Earth will perform an equally ambitious task. From its site in Chile, it will capture a panorama of the sky every few nights, creating a time-lapse of cosmic motion. Galaxies will drift, supernovae will flare, and subtle shifts in brightness will reveal the stretching of space. Combined with Roman and JWST, Rubin's data will show not just how the universe looks, but how it behaves. The European Space Agency's Euclid mission, already in operation, complements these efforts from orbit. Its primary goal is to chart how dark energy influences the clustering of galaxies, a test of whether the force accelerating the universe is constant, dynamic, or something entirely new. By measuring billions of galaxies up to 10 billion light-years away, Euclid will act as a bridge between local measurements and the distant cosmic microwave background. This collaboration among observatories represents a transformation in science itself. Cosmology used to rely on individual breakthroughs. One telescope, one discovery, one name in history. Now it has become a networked enterprise, a symphony of instruments tuned to the same question: what is the true shape of time? To complement these optical missions, a new field called multi-messenger astronomy is emerging. It combines light with other carriers of information: gravitational waves, neutrinos, cosmic rays. Each messenger tells a different part of the story. When two neutron stars collide, for example, they produce a flash of light and a burst of gravitational waves. The light reveals how far away the explosion occurred. The waves reveal how strong the event truly was. Comparing the two gives a direct, independent measure of distance. No need for ladders or calibrations. These cosmic standard sirens may soon become one of the most reliable rulers in the universe. Already, detectors such as LIGO, Virgo, and CAGRA have begun collecting these signals, and the future Einstein telescope and LISA, Laser Interferometer Space Antenna, will extend that reach across the cosmos. If enough standard sirens are recorded, they can build a parallel distance ladder, one that either confirms or contradicts current estimates of the Hubble constant. It is an entirely new method of testing the tension. There is beauty in this collaboration between extremes. Webb studies the faintest galaxies ever seen. LIGO listens to the tremors of space-time itself. Both instruments, one tuned to light, the other to vibration, are answering the same question: how fast is the universe changing? Back on Earth, researchers at universities and data centers translate those observations into models. They run computer simulations so vast that they mimic entire volumes of the cosmos, each filled with billions of particles of dark matter and gas. In these digital universes, they can vary the laws of physics slightly, increase dark energy here, slow down gravity there, and watch how the galaxies evolve. The goal is to find which simulation best matches reality. What these simulations often reveal is humbling. Even small adjustments to cosmic parameters can lead to universes that look radically different. Change the balance between matter and energy by a few percent, and galaxies might never form. Increase dark energy too quickly and stars are scattered before they can ignite. The fact that our universe sustains complexity at all, planets, chemistry, consciousness, seems to depend on an extraordinary fine-tuning of conditions. This fine-tuning may not be coincidence. Some scientists suspect that our universe is part of a larger multiverse, a vast ensemble of realities, each with different values for fundamental constants. Most of these universes would be sterile, unable to form atoms or life. We live in one that happens to be stable. In that sense, the Hubble tension might be a clue, a fingerprint of the deeper framework that selected our particular version of reality. Still, many physicists resist such ideas, preferring explanations that can be tested directly. For them, the solution must lie within our universe, hidden in the interplay between gravity and quantum fields. Perhaps the early cosmos contained unknown particles, relics that briefly altered the expansion rate before decaying away. Or perhaps time itself is not uniform but emergent, flowing differently in regions of high curvature or energy. These are not fantasies. They are the next logical steps in physics. Whatever the outcome, the coming decade will decide whether the Hubble tension is a measurement error, a new form of energy, or the first sign that the laws of nature themselves evolve. Each telescope, each detection, each line of code brings us closer to the answer. And as we watch the light of distant galaxies fade across the sky, we are reminded that all of this, the mathematics, the instruments, the wonder, originates from a single human question whispered to the stars. How does the universe keep time? The silence that follows is not empty. It is waiting to be filled with discovery. The next generation of astronomy will not rely on mirrors alone. It will rely on intelligence, both human and artificial. The questions raised by the Hubble tension are now so complex and the data so immense that no single observer can grasp it all. Every night, telescopes across the world generate terabytes of information: light from stars, spectra from galaxies, waveforms from black holes. Each data set is a fragment of truth, but it takes new forms of computation to weave those fragments together into a coherent story. That is why NASA and other agencies are building AI-assisted observatories capable of detecting patterns no human eye could recognize. Instead of scientists deciding where to look, algorithms now decide for them, scanning vast archives of data for anomalies, hidden correlations, or signatures of unknown physics. Machine learning systems are already identifying rare supernovae, classifying galaxies by shape, and predicting gravitational lensing events before they occur. At the heart of this revolution is the concept of real-time cosmology. In the past, astronomers observed the universe as if it were frozen. Snapshots of what once was now. With rapid computation and global coordination, they can watch change unfold as it happens. When a distant star explodes, signals travel through satellites, data centers, and neural networks within seconds, triggering follow-up observations from other instruments. The cosmos is becoming a living laboratory, its rhythms recorded in near real time. NASA's upcoming Lynx X-ray Observatory, for instance, will see the high-energy universe with sensitivity hundreds of times greater than previous missions. It will reveal how black holes inject energy into galaxies, how magnetic fields shape the evolution of gas, and how these processes affect the expansion of space itself. Meanwhile, the SPHER-EX mission will map the entire sky in infrared light, cataloging hundreds of millions of galaxies to trace the distribution of matter with unprecedented precision. Both missions, though very different, share the same goal: to refine the cosmic clock, to find out exactly how fast and why the universe grows. But the real leap will come when these observatories are linked together through quantum communication networks. NASA's Quantum Communications program is developing photon-based systems that can transmit data instantly and securely between telescopes and ground stations. In the near future, measurements made by one satellite could adjust another's instruments in real time, creating a feedback-driven network of cosmic observation. This would turn the entire solar system into a single, synchronized eye. On the ground, laboratories are pursuing the same precision through quantum sensors, devices capable of detecting infinitesimal shifts in space-time curvature or variations in gravitational potential. These sensors use entangled atoms to measure distortions 1 trillion times smaller than a human hair. If the laws of expansion are not constant, such instruments may catch them in the act, the faint heartbeat of the universe itself. The data produced by these systems will be staggering. But AI is learning to translate chaos into clarity. Neural networks trained on simulations can now estimate cosmological parameters in seconds, tasks that once took weeks of computation. Algorithms analyze distortions in galaxies, the faint glow of the cosmic web, and even the subtle statistical fingerprints of dark matter. What emerges is a portrait of the universe more detailed than anything humans alone could achieve. Yet as science gains precision, philosophy returns. The deeper the data goes, the more it confronts us with the same paradox. How can a mind existing inside the universe hope to measure the universe completely? Every measurement is shaped by the observer's position, every perspective limited by light and time. The Hubble tension, in a sense, is a mirror, a reminder that knowledge itself has an expansion rate. Some researchers are exploring ways to combine cosmology with cognitive science, studying how human perception influences scientific models. Even the algorithms we design reflect our assumptions about symmetry, stability, and order. Perhaps they suggest the next breakthrough will come not from a new telescope, but from a new way of thinking. Still, there is something profoundly human about the quest itself. To measure the expansion of the universe is to measure the distance between wonder and understanding. Each new instrument, from Hubble to JWST to the Roman telescope, extends not only our sight but our sense of belonging. The data may grow colder, but the reason we gather it remains warm, to see where we came from and where we are going. In practical terms, the Hubble tension is pushing the limits of cosmology toward a new synthesis. Physicists are beginning to merge quantum field theory with general relativity in computational models that simulate both the smallest and largest scales. These simulations no longer separate matter, radiation, and space-time. They treat them as interacting components of one vast dynamic system. Early tests already suggest that small quantum fluctuations in the early universe could have amplified expansion differently in different regions, potentially explaining why local measurements appear faster than global ones. If confirmed, this would mean that the cosmos is not expanding uniformly after all, that what we call the universe might contain subtle variations in the flow of time itself. Space would still stretch everywhere, but not at the same rate. The universe, in effect, might be swinging to its own rhythm, each region beating slightly out of sync with the rest. Such a revelation would not end cosmology, it would deepen it. It would suggest that time, far from being a background stage, is an actor in the play, one that responds to energy, matter, and information. And just as gravity bends space, perhaps information bends time. The tools being built now, quantum clocks, interferometers, AI pattern analyzers, are not just instruments for measurement, they are instruments for listening. They are teaching us to hear the harmonics of creation itself. The Hubble tension might one day vanish, resolved by clearer data and better models. But even if it does, the silence that follows will not be the end, because each answer in science opens the door to another question, and each measurement of the cosmos reminds us that we are part of what we are measuring. The future of cosmology is not a single discovery waiting to happen. It is a process, a feedback loop between curiosity and reality. And as long as that loop continues, the universe will never be silent. Every measurement of the cosmos is also a measurement of ourselves. The same equations that describe the curvature of space also describe the limits of our understanding. To study the Hubble tension, the discrepancy between what we see and what we expect, is to confront the most human condition of all: uncertainty. For centuries, humanity has sought a single, complete model of reality. From Newton's clockwork heavens to Einstein's space-time continuum, every generation believed it was closing the gap between knowledge and truth. Yet each discovery, rather than ending mystery, only deepened it. The more accurately we measure the universe, the less stable our picture becomes. The Hubble tension is not a flaw in that pursuit. It is the very sign that we are still capable of learning. When Edwin Hubble first observed the expansion of the universe in the 1920s, the revelation was devastating and liberating at once. It shattered the ancient idea of a static cosmos and replaced it with a living one, a universe still in motion, still becoming. Today's tension continues that revolution. It reminds us that the story is unfinished, that even with satellites and supercomputers, we are still standing on the edge of ignorance, staring outward with instruments that are, in essence, mirrors. The light that telescopes capture began its journey billions of years ago, long before the Earth formed. Each photon carries a history of collisions, absorptions, and re-emissions, a biography of the universe written in wavelength. When that light enters our detectors, it completes a loop across cosmic time. The moment we interpret it, the past becomes present again. Science, in that sense, is not merely observation, it is resurrection. Yet the meaning of this resurrection has changed. In earlier ages, the night sky inspired myths, constellations shaped from human stories. Now it inspires algorithms and spectra, but the impulse is the same: to find pattern, to locate ourselves within something larger. Even the term cosmology combines order, cosmos, with word, logos, the search to make sense of order itself. The Hubble tension adds a twist to that search. It tells us that there may not be one single order. Reality could be layered, its constants flexible, its rhythms local rather than universal. For many, this idea is unsettling. For others, it is thrilling, a reminder that the universe is still wild, that our models are maps, not territories. Consider what it means for civilization. Every time our vision of the universe changes, so does our vision of ourselves. The Copernican shift displaced humanity from the center of the cosmos. Relativity displaced the idea of absolute space and time. Quantum theory displaced the notion of certainty itself. The Hubble tension may now be preparing to displace something even deeper: the belief that reality is uniform. If the expansion rate truly varies across space or time, then we inhabit a cosmos with regional identities, each evolving at its own pace. The night sky we see could be older or younger in subtle ways than the sky seen from another galaxy. Time would no longer be a single river, but a braided delta, flowing differently across the landscape of the universe. This idea changes nothing in daily life, and yet it changes everything. Because to live in a universe with variable time is to live in one that refuses final answers. It means that progress, both scientific and human, is not a straight line, but an unfolding conversation. Each generation recalibrates the clock, adjusts the constants, and leaves behind a better approximation of truth. Even technology reflects that rhythm. The same instruments that measure cosmic expansion, atomic clocks, laser interferometers, AI-driven telescopes, are also used to synchronize the digital world we inhabit. GPS satellites correct for relativity. Quantum sensors detect gravitational shifts that affect communications. Without understanding the behavior of space-time, civilization itself would lose coordination. In a literal sense, society runs on cosmology. And yet, there is a deeper resonance. The drive to measure expansion mirrors our own expansion, of awareness, of compassion, of perspective. Each new telescope extends not only human sight but human empathy, reminding us how small and fragile our world is in the ocean of space. The same data that define galaxies also define us as a species capable of awe. Some philosophers now argue that science has replaced mythology not by destroying it, but by transforming it. Where ancient myths told stories about gods creating order from chaos, cosmology tells the same story in equations. Gravity and dark energy play the roles once reserved for deities. The Big Bang is a modern genesis, yet the emotional core is unchanged, a longing to understand where order begins and ends. Perhaps that is why the Hubble tension has captured such attention. It is not just a technical dispute about numbers, it is a question about whether the universe is knowable in principle. If two perfectly valid measurements disagree, what does that say about truth itself? Is truth a single value, or is it an evolving relationship between observation and theory? The answer may never be final, but the search, the act of comparing, refining, questioning, is what keeps science alive. The universe expands, and so does comprehension. The tension between them is the pulse of discovery. In the future, when historians look back at this century of astronomy, they may not remember the exact value of the Hubble constant. They will remember that we noticed the discrepancy. that we cared enough to ask why. That act of curiosity is what defines intelligence, whether human or cosmic. Because in the end, the story of the universe is not only written in starlight, it is written in the questions that light inspires, in the minds that refuse to stop measuring, even when the result does not fit. The Hubble tension is not a flaw in the cosmic design, it is the sound of reality breathing. Every scientific era ends the same way it begins, with a question that refuses to fade. The Hubble tension began as a technical discrepancy, a few kilometers per second per megaparsec that would not align. But over time, it has become a symbol of something far larger, the edge of knowledge itself. When two measurements disagree, one from the early universe, one from the nearby cosmos, it is as if the universe is whispering in two languages. Both are true, yet neither complete. The photons captured by JWST, Euclid, and the Hubble telescope speak of a cosmos expanding faster than expected, the microwaves echoing from the Big Bang, recorded by Planck and WMAP, tell of a slower, more deliberate unfolding. Between those two voices lies the silence that defines discovery. The solution may come from physics we have not yet written, or from mathematics that already exists but has not been recognized in nature. Some theories propose early dark energy, a brief burst of repulsive force that accelerated expansion shortly after recombination. Others suggest decaying dark matter, or a new kind of particle that altered the balance between radiation and mass. Each possibility is like a new note in a cosmic chord that has not yet been resolved. Whatever the answer, the process of searching reshapes us. It forces collaboration on a scale humanity has rarely achieved. Data from telescopes orbiting millions of kilometers apart must align with experiments conducted in vacuum chambers on Earth. Timekeeping, precision, humility. These become our tools as much as mirrors and lenses. The Hubble tension is not just a mystery, it is an act of unity. And yet, there is something deeply poetic in the idea that the universe itself resists simplification. Every time science approaches closure, reality opens another door. Expansion, entropy, uncertainty. These are not obstacles to understanding, but the very texture of existence. Perhaps the cosmos does not wish to be solved, only witnessed. The deeper we look, the more fragile our position becomes. Earth orbits a minor star, in a minor arm of a minor galaxy. Yet from that small vantage point, consciousness has reached backward 13.8 billion years. Through instruments of glass and silicon, a species that once measured seasons by shadows now measures space-time by starlight. The contrast is staggering and beautiful. This beauty is not sentiment. It is a form of accuracy. To describe the universe honestly, one must include wonder as a variable. The numbers alone cannot hold it. The redshifts, the spectral lines, the constants, all of them point to a universe that is alive with possibility, structured but not static, lawful but not closed. The Hubble tension, like every paradox before it, is not a crack in knowledge but a window. As we move into the coming decades, new missions will join the search. The Roman telescope will chart dark energy's fingerprints across billions of galaxies. The Einstein telescope will listen for gravitational whispers from before light itself. The LISA mission will track ripples between black holes across cosmic distances. Each will bring more precision, and with it, more questions. The closer we get to truth, the faster it recedes, like light outrunning its own reflection. But this is not futility. It is the rhythm of discovery. Every correction, every refinement, every paradox becomes a part of the larger narrative. A story not of domination, but of participation. We do not stand apart from the universe we study. We are one of its expressions, measuring itself through thought. If the Hubble tension endures, perhaps it means the cosmos is not governed by a single constant after all. Maybe its expansion is alive, responsive, a feedback system between energy, geometry, and time. That would make the universe less like a machine and more like an organism, evolving, self-adjusting, aware in some mathematical sense of its own parameters. In that view, cosmology becomes not the study of something distant, but the study of being itself. Light, gravity, and information are not separate phenomena, but facets of one continuous field, a field that, by observing itself, becomes more structured. And in that recursive act, consciousness emerges. We may never know whether the universe intended this, or whether intention is even a meaningful term at such scales, but we can know this: the expansion we measure outside mirrors the expansion within. The more we learn about the cosmos, the more the boundaries of the mind stretch to contain it. When future astronomers recalibrate their instruments and the Hubble tension finally finds resolution, whether through new physics or new precision, it will not end the story. The discovery will simply move the question elsewhere, to new frontiers of measurement, new conflicts between model and observation. That is how science breathes. Perhaps then, the true constant of the universe is not its rate of expansion, but its capacity for self-renewal. A cosmos that creates beings capable of measuring it has already transcended stillness. The numbers are only the echo of that awakening. So, as JWST peers deeper into the red dawn of time, it is not only looking backward, it is looking at the process that made looking possible. The light it receives is ancient, but the meaning it creates is new. Between those two, the universe becomes aware of itself for the first time, again and again. In that sense, the Hubble tension is not a problem to solve. It is a reminder that even in a universe ruled by gravity and expansion, the most powerful force remains curiosity. And in the quiet hum of data, in the light from galaxies that should not yet exist, the cosmos whispers the same message it has always whispered, across all time and all observation. Keep looking. Every new observation begins as a correction of the last. In the decades after Hubble's discovery, astronomers refined, recalibrated, and still the numbers drifted. When the James Webb Space Telescope turned its mirror toward the faintest galaxies, it expected confirmation. Instead, it delivered more tension. The early universe looked brighter, denser, and older than it should have. The light curves from distant supernovae implied one expansion rate. The microwave background, another. Between them lies a margin too wide to ignore and too precise to dismiss. This margin has become the echo of measurement. Teams across NASA, ESA, and independent institutes now rebuild the chain of assumptions one link at a time. Distances, redshifts, stellar ages, calibration stars, instrument drift. Each link appears solid, yet the chain refuses to close. The beauty of the problem is that every attempt to fix it deepens our understanding of the cosmos. To resolve a discrepancy of a few percent, one must rethink how light travels, how gravity bends, how time itself stretches. When Webb captures the faint glimmer of a galaxy 10 billion light-years away, that light has crossed a changing universe. Space has expanded, photons have cooled, and matter has shifted through dark filaments like ink in water. Correcting for those distortions is an act of reconstruction, not simply seeing, but rebuilding what was. The tension might therefore be telling us less about instruments and more about the medium through which light moves. Some physicists suspect subtle interactions between photons and dark matter could slightly delay or accelerate the apparent redshift. Others model a running gravitational constant, a law that drifts minutely as energy densities change. None of these ideas have yet replaced the standard model, but each forces new precision into the language of cosmology. Meanwhile, laboratory experiments mimic the cosmos in miniature inside cryogenic chambers. Lasers trap atoms in optical lattices, simulating gravitational potentials on nanoscales. These quantum analogs allow scientists to test whether fundamental constants remain constant under extreme conditions. If even one varies by a fraction, the whole picture of expansion could shift. The smallest fluctuation in an atomic clock could echo across billions of years of cosmic time. What makes this pursuit extraordinary is its humility. To solve the largest mystery known, we study the smallest measurable difference. Expansion, gravity, and quantum uncertainty meet at the limit of perception. And in that overlap lies a philosophical truth. Precision is another form of faith. Faith that nature, however vast, obeys principles we can uncover. The Hubble Tension has already transformed cosmology from a field of confident prediction into one of disciplined doubt conferences, now open not with conclusions, but with probabilities, error bars, and caveats. The tone is not defeat, it is maturity. The universe, it turns out, is subtle enough to reward patience. At the same time, this humility drives engineering forward. To detect deviations of a few kilometers per second per megaparsec, instruments must reach impossible stability. Atomic interferometers now measure time to within a few parts in 10 to the 18th power. Laser metrology aboard satellites synchronizes to femtoseconds. Every improvement made to understand the cosmos filters down into technologies that shape daily life: navigation, communication, medicine. The search for cosmic truth quietly builds the infrastructure of civilization. Yet the most compelling outcome of the tension may be conceptual. If expansion is not uniform, then our portion of the universe could differ slightly from another region far beyond visibility. We may live in a cosmic neighborhood with its own local curvature, its own tempo of time. In such a picture, there is no single true expansion rate, only perspectives embedded in a vast continuum. It is not that the universe contradicts itself. It is that we have finally reached the scale where local and global no longer align. This realization reshapes our metaphors. The cosmos is not a balloon stretching evenly, but a sea with currents, eddies, and tides. Galaxies are not dots on the surface. They are vessels carried by flows of geometry. The Hubble tension, then, is the wake of those invisible tides, a sign that space-time itself moves with more complexity than we imagined. To the next generation of astronomers, this mystery will be an inheritance rather than an obstacle. They will not seek a single constant, but a dynamic framework where change is expected. The universe may expand faster here, slower there, oscillating over eons in a cosmic rhythm too grand for any one epoch to perceive. Perhaps one day, when instruments reach the edge of measurable precision, the tension will fade, replaced by a new paradox. But even if that happens, the legacy of this era will endure. The idea that disagreement is fertile ground, that truth expands like the cosmos it describes. The next frontier in cosmology lies not in new constants, but in new connections. The data gathered from Webb, Euclid, and Roman are already being cross-referenced with gravitational wave maps, neutrino observatories, and cosmic ray detectors. This integration marks a shift from observation to orchestration, a symphony of messengers instead of a single line of sight. Each signal offers a different tempo of the universe's history. Light shows us the visible matter. Gravitational waves reveal collisions invisible to optics. Neutrinos whisper from the hearts of stars. Radio emissions trace magnetic webs across intergalactic voids. Combining them transforms the picture of expansion from a single graph into a living, multidimensional field. In that field, patterns begin to emerge, hints that regions of space evolve in correlated ways, like chords in a song. Some researchers propose that information transfer across cosmic structures could regulate expansion indirectly, a feedback network linking energy and geometry. It is speculation, but grounded speculation. The mathematics already resembles the network theory used to describe ecosystems and neural systems. If this vision proves true, then the Hubble tension is not a failure of measurement, but the first glimpse of a deeper order. What we call discrepancy may simply be the imprint of interaction on a cosmic scale. The same principle that governs biological feedback, balance through exchange, could govern the universe itself. And once again, the human parallel emerges. Our species thrives by exchanging information, refining models, adapting. Civilization is a microcosm of the cosmic method. Observe, compare, adjust, continue. The universe does the same through radiation, gravity, and time. In both, stability arises not from perfection, but from constant recalibration. Looking ahead, missions like LISA, CMB-S4, and the Einstein probe will extend this calibration across new frequencies. They will test whether the early universe followed exactly the same laws as today's, or whether time itself carries a slow drift, a cosmological evolution of physics. Even a slight difference could explain the tension and reveal that constants are not timeless but historical. If that proves so, our understanding of reality will shift from static law to evolving relationship. Physics would become history written in equations. The universe, once thought to be governed by eternal principles, would join the category of living systems, learning, adjusting, expanding not just in size, but in depth. In the end, the Hubble tension may be remembered as the turning point when cosmology embraced imperfection as a signal rather than noise. For the first time, scientists speak of the universe not as a solved mechanism, but as a narrative, one that invites participation, not closure. And as long as humanity keeps watching the faint glow between galaxies, as long as new telescopes open their mirrors to the dark, that narrative continues. Because what expands with the universe is not only space, but awareness. The numbers will change, the constants will evolve, and yet one truth will remain. The universe is unfinished, and so are we. Every era of science inherits a frontier it cannot yet cross. For Newton, it was the mystery of motion itself, why gravity acted at a distance. For Einstein, it was the reconciliation of gravity and quantum theory. For us, it is expansion. The Hubble tension defines the edge of comprehension, the fine line between what we can measure and what we can only infer. But edges are not limits, they are invitations. Each new telescope extends our reach not just spatially, but conceptually. The deeper we look, the more reality demands new languages. The Webb telescope has already pushed cosmology into a new dialect, one that mixes observation with imagination, data with doubt, precision with poetry. The images Webb sends back are not mere photographs, they are time machines. Every pixel contains a conversation between light and gravity that began billions of years ago. When we see a galaxy from 13 billion light years away, we are not observing something far. We are observing something long ago. The light we capture today departed before Earth existed. It crossed a universe still forming its first stars, still learning the meaning of transparency. That light now meets detectors chilled to near absolute zero. Engineered atoms that whisper their findings across vacuum and code. From that whisper, cosmology extracts a story about expansion, evolution, and entropy. The Hubble tension arises because that story no longer fits neatly together. The cosmic microwave background tells us that the early universe expanded at a calm, steady rate. Yet the nearby universe insists the pace has quickened. Either our local measurements are distorted by unseen mass, or the cosmos has changed its rhythm. Both options are profound. Either we misunderstand the scaffolding around us, or the laws we thought eternal are slowly evolving. No single equation will settle this easily. Instead, the resolution may come from a new framework that treats the universe not as static geometry, but as a living computation, an information process unfolding across energy fields. In such a model, expansion is not driven by a constant force, but by an adaptive one, an emergent property of how matter organizes itself. Recent studies of quantum entanglement hint at this possibility. The structure of space-time itself may arise from relationships between particles, from networks of information rather than a continuous fabric. If that is true, then as information flows change, so too does the apparent rate of expansion. The Hubble tension could then be the first empirical sign that space and time are products of information dynamics, not eternal backgrounds. This concept, once purely theoretical, now attracts real mathematical rigor. Simulations suggest that networks governed by entanglement rules can spontaneously expand, self-stabilize, and even mimic cosmic inflation. The resemblance is more than coincidence. It hints that the universe may not just evolve in time, but that time itself evolves. Still, evidence must lead emotion. Data is the judge, not the dream. And so, the scientific community continues its patient recalibration. Astronomers cross-check standard candles, reanalyze Cepheid variables, and refine models of cosmic dust that could bias luminosity. Each adjustment brings us closer, but the gap persists. It is small, only a few percent. Yet in cosmology, a few percent is an earthquake. Meanwhile, theoretical physicists explore the edges of dark energy, testing whether it behaves like a cosmological constant or something more dynamic. Some posit that it might interact weakly with dark matter, exchanging momentum in ways that subtly alter cosmic expansion. Others explore early-time scalar fields, ephemeral energies that may have temporarily changed the pace of the Big Bang. These are not science fiction. They are peer-reviewed, mathematically consistent attempts to explain the same data in different lights. But each carries implications so vast that confirmation would rewrite textbooks. If early dark energy existed, then the universe we inhabit is not just older or younger, it is more complicated in its infancy. If gravitational constants evolve, then Einstein's elegant equations are approximations of a deeper order. And if local curvature variations explain the tension, then our visible universe is a cosmic peninsula jutting into a sea of unseen geometry. The truth could also be all of these at once. Nature often blends solutions. What we call paradox may simply be the overlap of partial truths, like multiple instruments playing the same melody slightly out of tune. The harmony exists even if our hearing has not yet caught up. To scientists who spend lifetimes refining decimals, this tension is not frustration. It is exhilaration. It means the universe is still teaching. It means observation still matters. It means that the next generation of telescopes will not merely confirm, they will surprise. Among those future instruments, the Nancy Grace Roman Space Telescope will measure distant supernovae with unmatched precision. The square-kilometer array will map hydrogen's faint radio glow across epochs. And when combined with gravitational wave observations, these data streams will triangulate expansion in 3 dimensions: time, distance, and motion. This is the dream of 21st century cosmology, to transform the universe from image to instrument, to read it as one grand symphony of forces echoing through space-time. The Hubble Tension is only the first discordant note that reveals how vast the composition truly is. Yet beyond equations and models, this quest reveals something about the human condition. Our curiosity expands just as space does, not uniformly, but in bursts, accelerating when boundaries are discovered. Each paradox ignites a new field, each anomaly births a new idea. In that sense, the Hubble tension is not a flaw in science but its essence, because science, like the universe it studies, thrives on tension, the dynamic between what is known and what remains to be known. The expansion we measure beyond the galaxies mirrors the expansion within consciousness. Both are the same process seen from 2 scales: energy seeking expression, structure seeking understanding. And perhaps this is the real meaning hidden beneath the data, not that the universe is inconsistent, but that it is alive with potential, responsive to inquiry, generous with questions. If the cosmos could speak, its message might sound familiar. Not certainty, not finality, but invitation. Keep looking. Measure again. Think deeper. Because somewhere between the flicker of ancient light and the hum of our detectors, between the silence of the void and the noise of human thought, lies the answer. Not to how the universe expands, but why it allows itself to be known at all. Every new generation of instruments makes one fact increasingly difficult to ignore. The constant that governs cosmic expansion does not behave like something carved into the foundation of physics. It behaves like something participating in the evolution of the universe itself. The idea once seemed heretical, a violation of the elegant stillness many believed was woven into the laws of nature. Yet the data continues to gather, persistent and quiet, like an ocean tide pushing against a rigid shore. Slowly the boundary moves. The measurements taken from distant supernovae suggest that the rate of expansion today is different from what the early universe would predict. If the cosmic expansion rate was truly fixed, then ancient light and modern light would tell the same story. They do not. The difference is small enough to be invisible to everyday intuition, yet large enough to reshape cosmology. A few percent discrepancy becomes a signal of profound meaning when scaled across billions of years. Some scientists now consider whether the constant is not constant at all. In this interpretation, the force driving the expansion of space may have shifted over time, responding to conditions that existed only in the early cosmos. It is as if the universe exhaled with a slightly different rhythm when it was young. Perhaps the symmetry of space-time itself evolved as matter condensed, cooled, and organized. If so, the Hubble tension is not a conflict within the data, but a letter from an earlier epoch written in a dialect modern physics is still learning to read. This concept gains traction from the behavior of other physical constants. The fine structure constant, for example, governs the strength of electromagnetic interactions. While laboratory tests show it to be stable across human time, observations of ancient quasars hint at slight spatial variations. These variations are incredibly small, barely measurable, but they challenge the assumption that the fabric of physics is uniform. If one constant can drift, even by a fraction of a percent, then others might too. The cosmos may be governed by fields that evolve slowly, subtly, across the arc of cosmic history. In this view, dark energy becomes less like a mysterious pressure and more like a dynamic field permeating space, adjusting as conditions change. This aligns with certain early universe models in which scalar fields shaped cosmic inflation. These fields, once responsible for the rapid expansion fractionally after the Big Bang, may have left behind faint remnants that continue to influence cosmic evolution. Such remnants would not appear in simple models. They would manifest only when precision reaches the level Webb and future missions now achieve. If dark energy truly evolves, its evolution would ripple outward across cosmic time, altering the formation of galaxies and the structure of the cosmic web. Regions with slightly different expansion rates would create subtle distortions in the distribution of matter. These distortions may already be visible in weak gravitational lensing measurements, where the bending of light reveals the hidden mass shaping the foreground. Some maps show unexpected smoothness or sharpness in certain areas. These anomalies may reflect the fingerprints of an evolving cosmic field. Meanwhile, gravitational wave observatories offer an entirely different window into the problem. When distant neutron stars or black holes merge, they release waves that stretch and compress space-time as they travel. By comparing the distance inferred from the wave's amplitude with the redshift measured from accompanying light, researchers gain a new way to measure expansion. These so-called standard sirens are unaffected by the complexities of supernova models or local dust interference. Early detections already suggest slight deviations from established expansion values. As sensitivity improves, these waves may provide the cleanest measurement of expansion in the entire field of astronomy. Such independent measurements will be essential, because the implications extend beyond astrophysics. If the rate of expansion depends on the state of the universe, then time itself becomes conditional. The flow of time, usually treated as uniform, would depend on how energy is arranged. This possibility is not new. Relativity already teaches that time bends and stretches in the presence of mass and motion. But an expansion rate that changes introduces a deeper point. Time may not only respond to gravity, it may evolve with the universe as a whole. This idea intersects with research into quantum information. Some physicists propose that space-time geometry arises from networks of entangled particles. In this framework, the shape of the universe is not a pre-existing substance, but an emergent property of relationships. When those relationships shift, the geometry shifts with them. Expansion may then reflect changes in the density of information, not simply the stretching of physical space. The Hubble tension would then become a natural consequence of the universe transitioning from one informational regime to another. At first glance, this sounds abstract, almost philosophical, but it connects directly to measurable effects. If geometry emerges from entanglement, then any process that alters entanglement density should leave traces in large-scale structure. Simulations show that slight variations in entanglement distribution can produce cosmic structures resembling observed anomalies, including low-density voids and unexpected galactic alignments. These patterns become more pronounced at high redshifts, exactly where Webb discovers its most surprising galaxies. Yet none of these interpretations render earlier models obsolete. Classical cosmology remains accurate over most scales. The new ideas refine rather than replace. The universe still expands. gravity still governs structure. Light still travels along geodesics carved by mass. But the edges of the model, the places where precision becomes essential, reveal deeper layers. The surface remains familiar while the foundation grows richer. This is the hallmark of genuine scientific progress. The goal is not to discard old knowledge, but to integrate it into broader frameworks. Einstein did not erase Newton. He extended Newton's laws into realms they could not reach. Likewise, the next era of cosmology may not erase the standard model, but embed it within a more flexible architecture. The Hubble tension is the fracture through which that architecture becomes visible. To explore this architecture, new missions are forming. The Roman telescope will survey millions of galaxies with an accuracy unmatched by any previous instrument. The Euclid mission will map dark matter distribution across cosmic history. Future gravitational wave networks will measure distances across billions of light years. These tools are not isolated. They are pieces of a single system designed to triangulate reality from multiple angles. Even now, the convergence of these data streams suggests a shift. The expansion rate may not be one number but a curve, a history written across time. The tension between early and late measurements then becomes a natural feature of evolution. The universe is not static, it breathes. Not in a biological sense, but in a dynamic one. Energy redistributes, fields settle, matter organizes, and the geometry responds. This dynamic view restores mystery to a cosmos once thought solved. The universe becomes a story still being written, not a finished structure. Every new measurement becomes a sentence in that story. Some sentences contradict earlier interpretations, others clarify. The Hubble tension, then, is not an error. It is the plot twist revealing that the narrative is far more complex than assumed. The challenge is to follow the thread without imposing meaning prematurely. Science moves through patience, not haste, and so researchers continue to observe, calculate, refine, and revise. Each correction adds detail. Each anomaly adds depth. The universe grows sharper not by agreeing with expectations, but by resisting them. In this resistance, cosmology finds purpose. A field without mysteries would stagnate. A universe without tension would offer no invitation to explore. The expansion problem ensures that curiosity remains active. It ensures that technology advances. It ensures that theory evolves. And it ensures that humanity continues to look upward not only for answers, but for direction. The deeper the measurements reach, the more clearly the pattern emerges. The tension in the expansion rate is not a flaw in the instruments or a misstep in the equations. It is a signature of transition woven into the structure of the universe itself. Every dataset, every anomaly, every recalculated constant points to the same quiet conclusion. The cosmos is not a fixed machine humming with eternal regularity. It is an evolving architecture, responding to its own conditions across time. What began as a small disagreement between early universe predictions and modern observations has grown into a bridge between two eras of physics. On one side lies the classical picture, in which the cosmic expansion rate is treated as an immutable quantity set at the beginning of time. On the other side lies an emerging view in which the expansion rate mirrors the rhythm of the universe as it cools, structures form, and energy redistributes. The tension between these views is not a contradiction but a hinge, guiding cosmology toward a broader understanding. Webb's early discoveries accelerate this transition. Its precision reveals galaxies forming earlier, brighter, and more mature than expected. These systems contain far more mass and complexity than classical timelines permit. Every luminous arc and compact starburst region Webb captures becomes additional evidence that conditions in the early cosmos were not only extreme, but rapidly shifting. The expansion rate implied by early light differs because the environment that produced that light differed. The early universe was hotter, denser, more turbulent, and likely governed by fields that no longer dominate. As instruments refine the story, the apparent conflict between different measurements weakens. The numbers do not collide. They curve toward a common explanation. The discrepancy becomes a contour of evolution, not a flaw. Just as the temperature of the cosmic microwave background records the cooling of space, the tension records the adjustment of the underlying forces that shaped that cooling. The constant was never constant. It was a measurement taken at two very different cosmological temperatures. Simulations support this emerging coherence. When researchers incorporate evolving dark energy fields or modify the physics of primordial density fluctuations, the predicted expansion rates across time become smoother and more consistent with observations. Models that once required unnatural fine-tuning now behave more naturally. The universe begins to make sense at multiple scales, from the faint glow of the first atoms to the vast lattice of galaxies stretching across billions of light years. Although the details remain uncertain, the general direction is unmistakable. Cosmology is moving toward a picture in which expansion is a variable shaped by energy distribution, matter clustering, and the subtle remnants of forces active only in the first instance of creation. This picture does not reject the successes of earlier models. It extends them, offering a framework in which the early cosmos and the present cosmos are two chapters of a single evolution rather than two isolated conditions connected by a straight line. As this framework develops, the importance of precision grows. Every photon web collects, and every gravitational wave detected by new observatories strengthens the bridge between theory and reality. The cosmic expansion rate becomes less a number and more a profile, a history written in the stretching of light. The tension that once threatened to disrupt cosmology now anchors its progress, encouraging more careful measurements, more sophisticated models, and more ambitious missions. The next generation of instruments is designed to resolve the structure of this evolution in even finer detail. The Roman telescope will map millions of galaxies, revealing the geometry of space with unprecedented clarity. Euclid's dark matter surveys will trace how invisible mass shapes cosmic expansion. Gravitational wave networks will provide independent distance measurements across vast stretches of time. Together, these observations will allow scientists to reconstruct the expansion history of the universe with the accuracy of a geological map, charting ridges, valleys, and transitions across billions of years. In this emerging view, the Hubble tension becomes a turning point, not an obstacle, but a landmark. The moment when cosmology stepped beyond the assumption that the universe behaves like a simple equation and embraced the idea that it behaves like a system undergoing long-term change. The laws remain consistent, the environment changes, and the interaction between the two produces the small divergences that accumulate into the tension we measure today. What is most striking is how natural this dynamic interpretation feels when placed alongside everything else we know. Stars evolve, galaxies evolve, chemical abundances evolve. Even the large-scale geometry of space-time changes as mass moves. Why should the cosmic expansion rate be the only quantity exempt from evolution? The tension reminds us that constancy in physics does not always mean immobility. It often means consistency in the rules governing change. This shift reverberates beyond cosmology. It influences how physicists think about fundamental forces, the origin of structure, and the informational nature of space-time. If expansion evolves, then the boundary between geometry and energy becomes more porous. Fields become storytellers of cosmic history. Structure becomes a record of interactions layered across time. And the universe becomes a dynamic system whose present state cannot be divorced from its past. At the human scale, this perspective offers a kind of calm clarity. The cosmos is not a static backdrop against which events unfold. It is a participant in its own story, shaped by feedback, transition, and the slow interplay of forces. The expansion rate is one of its voices. When that voice shifts, it signals that something in the underlying harmony has changed. The task of science is not to silence the shift, but to understand it. Every major advance in astronomy began with a tension like this. The slight wobble of Mercury's orbit led to general relativity. The faint hiss of microwave radiation revealed the echo of the Big Bang. The accelerated expansion discovered in supernovae unveiled dark energy. Now the discrepancy in the expansion rate points toward the next refinement in our understanding of the universe's architecture. As the picture grows sharper, the tension becomes less a problem and more a guide. It tells researchers where to look, which assumptions to test, and which models carry hidden limitations. It pushes instruments to their limits and inspires new theories capable of capturing greater nuance. Through this quiet pressure, it shapes the science that interprets it. In this sense, the Hubble tension becomes a bridge between eras of physics. It connects the known with the unknown, the measured with the inferred, the present universe with its distant past. It reminds us that certainty in science is never the absence of anomalies, but the willingness to follow them. The universe has never been silent. It speaks through light, through motion, through structure, and now through the slight mismatch of two numbers that refuse to align perfectly. As observations continue and models evolve, the story of cosmic expansion will become clearer. The constant will settle into its rightful place as a parameter shaped by cosmic history. The tension will fade, not because it was an error, but because it was understood. And cosmology will carry forward with a deeper appreciation of the universe as a dynamic, unfolding system. The expansion of space, once thought simple, becomes a record of everything the cosmos has endured. The first stars, the birth of galaxies, the influence of dark matter, the quiet acceleration driven by dark energy, and the gradual cooling of the background radiation all contribute to the pattern inscribed in the constant. To study that pattern is to study the life of the universe itself. In that sense, the Hubble tension is not a crisis. It is a moment of recognition, a reminder that the cosmos still has layers left to reveal, and that each discovery is an invitation to refine humanity's understanding of the place it inhabits. The universe continues to expand, and with it expands the horizon of knowledge.